Hello and welcome to my talk. My name is Ulrike Kuhl, and in this video it is my pleasure to present to you our work, Keep Your Friends Close and Your Counterfactuals Closer, Improved Learning from Closest rather than Plausible Counterfactual Explanations in an Abstract Setting. Our work is rooted in the field of explainable AI, and to motivate the issue, I would like to start with something that is probably familiar for all of us. In our daily interactions with other humans, we often use explanations. For us as human beings, this serves an important purpose. Explanations improve our understanding of one another and the world, so we can build up more stable mental models that allow for better prediction and control. When automated systems explain their decisions to the end user, however, much is still lost in translation. And this leads us to the central question of explainable AI. How can we effectively explain decisions of automated systems to the end user? In light of this question, a seminal review by Tim Miller gave rise to a user-centered focus on explainability. They advocate that we need to be inspired by the human explanation process to generate effective explanations for human users. So the idea is to take human explanations as an example, come up with respective approaches to be implemented, to equip AI with human-like explanations. But what are characteristics of such human-like explanations? To learn something about how humans explain, we may turn to decades of psychology research on that issue. This research shows that human explanations are typically contrastive. They emphasize why a specific outcome occurred instead of another. And humans prefer explanations that are plausible, that is, in line with their current mental model of the world. This has led the community pretty quickly to consider one type of human-like explanation as particularly valuable, so-called counterfactual explanations, or CFEs. Counterfactuals are always post hoc, that is, they explain after a prediction was made why this prediction was made. And they work as explanation by highlighting conditions that would lead to an alternative outcome. As in this example, the robot tells us that if Y had happened, they would have done X. And the amazing thing is, counterfactuals can be computed relatively easily. They can be formalized as an optimization problem for a classifier. Specifically, we want to find an alternative XCF to the original input X that leads to a different desired outcome Y bar. And importantly, this problem is regularized in a way that the alternative XCF stays as close as possible to the original input. That is given by the regularization term theta here. This is the classical closest definition of CFEs. This approach is incredibly popular because CFEs like this are contrastive, as human explanations generally are. However, practically, this approach does not always produce solutions that are plausible. For instance, this original image gets labeled as a 4, and a closest CFE to change this label into a 0 looks like this. And I guess we can all agree that this is not a clear or sensible example of a 0, right? So to circumvent this issue, we can extend the original definition by a plausibility constraint formalized down here. This way, we make sure that produced CFEs belong to a set of plausible CFEs. For instance, we may limit the set of possible counterfactuals to the training data as a representative set of feasible examples. The idea with this approach is to have not just explanations that are contrastive, but also plausible. And theoretically, this is all nice and well, but what we do not know, does this constraint make automatically generated plausible CFEs also more usable for humans? And this corresponds to the research question of the current work. More specifically, we ask, do novice users benefit from a plausibility constraint of computing CFEs when tasked to gain new information from an unknown system in an abstract domain? And our main expectation was that, yes, users will probably work with them better, because by seeing more representative examples of the actual data set, they build a more appropriate mental model more quickly. To investigate this and similar questions empirically in user studies, we developed the Alien Zoo framework. In the Alien Zoo, users perform an iterative learning task presented as an engaging online game. In essence, users imagine themselves as zookeepers. As such, they need to select some plants to feed some aliens. And if the user made a good choice, the number of aliens increases. And if the choice was bad, the number decreases. The challenge here is users do not know what might be a good or bad choice. They need to figure that out by interacting with the game. And to give a little help, the system provides either closest or plausible CFEs at regular intervals. And this feedback highlights alternative choices that would have led to a better result in previous trials. You might wonder now, how did the system evaluate whether the user made a good or a bad choice? This is determined by an underlying machine learning model. Specifically, we first generated synthetic data according to the following scheme. The growth rate, determining how much the number of aliens grows or shrinks, is proportional to the value of plant 2 if and only if plant 4 has a value of either 1 or 2, or plant 5 is larger than 3. This synthetic data was then used to train a regression tree model. And this trained model was in turn used to predict the growth rate based on the user input during the actual game. So together with the game interface and this ML backbone, we have all the ingredients to run our user study. So let's go. First off, a look at the participants. We recruited users via Amazon Mechanical Turk, randomly assigned them to the group receiving closest CFEs or the group receiving plausible CFEs. In the final dataset, we evaluated data from 74 participants with 40 users in the closest and 34 users in the plausible condition. As a start, we also evaluated whether groups differed in terms of their demographic information. For this, we evaluated the age and gender to rule out any confounding effects, and we did not find any group differences here. So this gave us confidence to look at their performance in the Alien Zoo game. First off, were users able to make their pack of aliens grow? In this plot, we show for each trial on the x-axis, the average pack size per group on the y-axis, in blue for the closest group and in green for the plausible group. And we do see a significant main effect of group driven by performance differences in the last trials. Surprisingly though, it shows the reverse effect from what we actually expected. Users in the closest but not the plausible group generated larger pack sizes. Secondly, we considered time users needed to reach a feeding decision. Our expectation here was that users become more familiar with the system, the more automatic and the faster their decision-making would become. We did not observe a difference between the groups in terms of decision time, but taken together, all users became significantly faster in reaching a decision already after trial 1. This most likely shows that users took more time on the first decision to familiarize themselves with the interface. Last, we asked users to identify plants they thought were relevant or irrelevant for task success. In this way, we evaluated their explicit knowledge of the underlying data. To do so, we assessed the number of matches between user answers and the ground truth. Here, groups did not differ from each other, but they showed significantly better relevance judgments than expected by chance, especially when asked to identify plants that were not relevant. That's the item down below. So this shows that both groups formed some explicit knowledge of the underlying data distribution. Interestingly, the plausible group, but not the closest group, was also significantly above chance when identifying plants that were relevant. Still, also in the relevant case, groups did not significantly differ from each other. After playing the game, participants also completed a post-game survey. This was essential to assess the subjective usability of both CFE approaches on top of the objective task performance. Each plot on this slide represents one survey question and shows the percentage of users of each group selecting one of 5 Likert-style answers to the questions, ranging from strongly disagree to strongly agree. And first, we had to note that there was no significant group difference on any item. This is interesting because we do indeed see differences in terms of practical task performance. We saw that the closest group performed objectively better. However, this is in line with previous work. Objective measures of usability may actually deviate from subjective measures of usability. Since there are no significant differences, we should interpret these data with utmost caution. Still, I would like to comment on one interesting trend you can spot up here on top. When directly asked about helpfulness and usability of feedback, the closest group has a tendency to give higher ratings in line with their performance advantage. So what can we make out of this? Surprisingly, our initial hypothesis was proven flat out wrong. The data and statistics actually tell us that no, novice users do not benefit from a plausibility constraint given the current task and the setting. The opposite seems to be true, suggesting that the closest counterfactuals are actually more helpful. And how can we explain this? To find an answer, we can turn to psychology again. There are different notions of plausibility for humans, and one is comparative similarity. That means when humans generate counterfactuals they themselves consider plausible, they tend to deviate as little as possible from the real state. And that might explain what actually happened. We have a factual state represented by these 3 symbols. We also have a closed CFE that is only minimally different, but not actually part of the underlying data distribution. And we have a plausible CFE that deviates quite a bit from the factual state, but is part of the underlying data distribution. Then the closed CFE will elicit greater perceived plausibility and compared to the plausible CFE that is much more dissimilar from the factual state. So should we just forget all about plausibility constraint for CFEs? Well, we don't really know. What we can say with confidence is that closest CFEs seem to be more useful in the abstract domain for novice users that learn to discover. We cannot and should not, however, generalize to other domains, use cases, or user groups. For example, we find it very likely that users benefit greatly if they have some domain knowledge to rely on. We would posit that the situation looks a lot different for people who are already experts in feeding aliens, as they would be able to also evaluate an explanation in terms of the explanation's probability. And that's an exciting route for future research. Nevertheless, we can surely conclude novice users benefit more from the comparative similarity of closest CFEs in an abstract domain. Still, both groups show some learning, highlighting the value of interactive and goal-directed tasks for user evaluations, as can be seen in this Alien Zoo framework. And finally, we show here that research of explainable AI approaches need to bear in mind the human user, their behavior, their preferences, and their mental models to build effective explanations. And with this take-home message, I would like to close by mentioning that all code, data, and scripts are available at GitHub. And I would like to thank you very much for your attention.